Hello, everyone. Welcome.
Hello.
Hi, I'm Oliver.
Hi, I'm Lily.
Science in Easy English.
And today's question, what is dark matter really?
Okay, usually I like to ease us into a topic, maybe tell a joke, talk about the weather. But today we have to start with some numbers that, and I'm being serious, they kind of hurt my feelings.
Hurt your feelings, how so?
Yes, deeply. I was looking at this cosmic pie chart for today's deep dive, and it breaks down what the universe is actually made of.
Right.
And it turns out that ordinary matter, the stuff we can see and touch,
Mm.
me, you, stars, planets, pizza, my dog, all of it.
Mm-hmm.
That is only about 5% of the entire universe.
Just a tiny, tiny slice of the pie, that's right.
We are the minority. We're basically just the dust on the windshield of the cosmos, because the rest is 68% dark energy, which we are not even touching that today. My brain can't handle it. And roughly 27% is this thing we call dark matter.
It is a really humbling realization, isn't it? We think of ourselves and the stars as the main event, but physically, we are just a trace impurity. The main structure, the real bulk of the mass, is this invisible stuff.
So let's unpack this. We call it dark matter, which sounds very sci-fi, very ominous. Is dark even the right word for it?
Not really, no. Dark makes you think of a shadow or maybe a black t-shirt, but dark matter doesn't absorb light, it doesn't reflect light, and it doesn't emit light.
So if you could hold a chunk of it, it wouldn't be black.
It would be completely invisible.
Transparent.
So it's invisible matter.
Essentially, yes. It's transparent to every single sensor we have.
Okay, so if it's invisible and we can't touch it, how do we even know it's there? Are we just making this up to make the map work?
We know it's there because of gravity. It has mass. And because it has mass, it pulls on things. We can see regular matter stars, galaxies moving in ways that only make sense if there is a huge amount of invisible mass pulling on them. Right. And the mission for today isn't just to talk about the history of this ghost story. We're diving into this now because as of late 2025 and just this past January 2026, we have had a massive influx of new data.
It's a very, very exciting time for cosmology. We've had major updates from the James Webb Space Telescope, the Euclid mission, and a detector that's buried a mile underground in South Dakota. We are getting closer than ever.
So let's start with the big picture then, the evidence in the sky. We've been looking for this stuff for a long, long time.
We have. It really started back in the 1930s with an astronomer named Fritz Zwicky. He was looking at this huge cluster of galaxies, the Coma cluster.
Okay.
And he calculated how much mass they should have based on their light, just counting the stars. And then he measured how fast the galaxies were all zooming around.
And let me guess, the math didn't add up.
Not even close.
Yeah.
The galaxies were moving so incredibly fast that the cluster should have just flown apart. There wasn't enough visible gravity to hold it all together.
And he called it?
He called the missing stuff Dunkel Materie.
Which is just German for dark matter.
Oh, exactly. But, people didn't really believe him back then.
No, I heard he was a bit of a controversial character.
He was. So it took until the 1970s when an astronomer, Vera Rubin, looked at spiral galaxies. And she found that the stars at the very edge of the galaxy were spinning just as fast as the stars in the center.
Wait, hold on. Why is that weird?
Well, think about our solar system. Mercury is close to the sun. It orbits really fast. Pluto is way out there. It orbits very slowly. Gravity gets weaker the further out you go.
Okay, that makes sense.
So in a galaxy, the stars on the edge should be moving slower. But Rubin found they were all moving at basically the same speed.
So it's like if you spin a merry-go-round really fast, the kids on the edge are supposed to fly off.
That is a perfect analogy.
But in these galaxies, the kids on the edge were just hanging on.
They were hanging on tight. And that meant there had to be a massive, invisible halo of matter holding them in, providing all this extra gravity. That was the smoking gun.
Okay, so that's the history. But fast forward to right now, January 2026. The James Webb Space Telescope just dropped some new images.
Oh, yes. Last month, scientists released a new map of dark matter in a region of the sky called the Cosmos Field. Now, Hubble had mapped this before, back in 2007.
Right.
But this new map from James Webb is twice as sharp.
But again, if you can't see it, how on earth do you map it?
Well, we map it by seeing how its gravity distorts the light from behind it. But here's the real aha moment from the new map.
Okay.
It showed that dark matter and regular matter are perfectly aligned.
What does that mean, aligned?
It means that wherever we see a galaxy, we see a big clump of dark matter. It confirms that dark matter acts as the scaffolding, or like a cosmic web. Imagine a spider web in the morning dew.
Okay, I'm picturing it.
The dark matter is the silk threads, the structure itself, and the galaxies are just the tiny dewdrops clinging to that silk. The James Webb data shows us that the dew is sitting perfectly on the silk.
That is a beautiful visual. So without the dark matter web, the galaxies wouldn't have anywhere to form.
Precisely. The data shows this has been true throughout cosmic history. The dark matter clumped together first, and then it pulled all the regular gas in to form the stars we see. It is the invisible skeleton of the universe.
And speaking of maps, we have to talk about Euclid. This is the European Space Agency's telescope, right?
Yes. And while James Webb looks at these tiny patches in super high detail, Euclid is looking at the whole sky. It's often called a time machine.
Because it's looking back 10 billion years into the past.
Correct. And it just recently found 500 new gravitational lenses.
Okay, so let's unpack gravitational lensing. You mentioned it earlier, but how does it actually work?
Imagine you have a wine glass, and you place it on a newspaper. If you look through the stem of the glass, the words underneath look all distorted, right? Stretched into a curve or a ring.
Right, yeah, like a funhouse mirror.
That is exactly what dark matter does. It's so heavy that it literally warps the fabric of space-time itself, and it acts just like that glass stem. When light from a distant galaxy passes near a clump of dark matter, the light bends. We see the background galaxy as a smeared arc.
So by measuring how smeared the background galaxies are, we can calculate exactly how much invisible mass is sitting in the foreground.
You've got it. And with Euclid's wide view finding all these lenses and James Webb's sharp view analyzing them, we are building the ultimate 3D map of the invisible universe. We know where it is better than ever.
And this is where it gets really interesting. Knowing where it is, that's not the same as knowing what it is.
That is the million-dollar question. We have a map of the ghost, but we haven't actually caught the ghost yet.
So let's leave space and head deep underground. Because while the telescopes are mapping the sky, there are physicists sitting in an old gold mine in South Dakota trying to catch a particle.
This is the LZ experiment, or LUX Zeppelin. It's located 1 mile underground at the Sanford Underground Research Facility.
Why a gold mine? Why a mile underground? Are they hiding from something?
They are. They're hiding from cosmic rays. The surface of the Earth is constantly bombarded by noisy radiation from space. If you want to detect something as shy and weakly interacting as a dark matter particle, you need absolute silence. The mile of rock above them blocks out all that cosmic noise.
Wow. I read the elevator ride down there takes 10 minutes, just down into the dark.
It's a serious commute. And once you're down there, the detector is inside a massive water tank, which is inside a lead castle, all to shield it.
And the detector itself is just a giant bucket of liquid xenon.
Right. A very, very sophisticated bucket. It holds 10 tons of ultra-pure liquid xenon. The idea is that the universe is filled with these dark matter particles, specifically a type we call WIMPs.
Weakly interacting massive particles.
Right. And as the Earth moves through space, we should be flying through a sort of wind of these particles.
And the hope is that one of these WIMPs will just accidentally bump into a xenon atom.
That's the theory. If a WIMP hits a xenon nucleus, it should create a tiny flash of light and release some electrons. The LZ detector is basically a giant camera waiting for that one specific tiny flash in the dark.
Okay, so late last year, December 2025, they released the results from their first big science run. They analyzed data up to April 2025. So did they see the flash?
No, they saw nothing.
Wait, nothing. I feel like if I spent all that money and went down a mine shaft every day, I'd want to find something. Is that a failure?
It sounds disappointing, I know, but in science, a null result is actually incredibly powerful. They were looking for WIMPs in a very specific mass range between 3 and 9 GeV.
Whoa, pause. Giga-electron volts, is that like a battery size?
It's a unit of mass in particle physics. To give you a sense of scale, a proton is about 1 GeV. So they were looking for dark matter particles that are roughly 3 to 9 times heavier than a proton.
Okay, so they were looking for the medium-sized ghosts.
Exactly. And by finding nothing, they have ruled out that entire possibility. They've proven that dark matter isn't in that range.
Ah, so it's like looking for your keys. If you check the kitchen and they aren't there, you haven't found your keys, but you know you can stop looking in the kitchen.
That is the perfect way to look at it. We're just narrowing down the hiding spots.
Yeah.
But there was another twist in their data that's actually huge news.
The neutrino fog.
Yes, this is fascinating. Even though they didn't see dark matter, the detector was so sensitive that it did detect boron-8 solar neutrinos.
Particles coming from the sun.
Yes. Neutrinos are also ghost-like particles, but we know they exist.
Mm.
And detecting them in this kind of experiment is a massive engineering milestone. It proves the machine is the most sensitive detector ever built, but it introduces a huge problem.
The fog.
Right. Now that our detectors are sensitive enough to see neutrinos, those neutrinos become background noise. They can mimic the signal of dark matter. We have officially entered the neutrino fog.
Explain that to me. Why a fog?
Think of it this way. Imagine you're in a library, trying to hear a tiny whisper. That's dark matter. For years, the room was quiet. But now, the air conditioner is turned on. That's the neutrinos. The background hum is now louder than the whisper you're trying to hear.
And you can't exactly turn off the sun.
No, you cannot. So future searches are going to be much, much harder. We have to figure out how to distinguish a neutrino from the sun from a dark matter particle from the cosmos. We've hit a fundamental flaw in physics.
So if LZ didn't find these WIMPs and we're entering this fog, does that mean WIMPs are dead? Are we looking for the wrong thing?
WIMPs are definitely not dead, but the window is certainly closing on the light ones. The consensus is shifting a bit. Maybe they're heavier than we thought, or maybe they behave differently.
But WIMPs aren't the only suspect in the lineup anymore, are they? It feels like the search is getting a bit chaotic.
It is becoming a bit of a Wild West, yeah. Since the favorite child, the WIMP, hasn't shown up to the party, physicists are looking at other suspects. A really strong contender now is the Axion.
Axion, I swear that's a brand of laundry detergent.
You're not wrong. A physicist named Frank Wilczek actually named it after a detergent because he thought this particle would clean up a messy problem in physics.
No way! That is amazing.
But axions are totally different from WIMPs. They're super, super lightweight. If WIMPs are bowling balls, axions are more like feathers.
And how do you hunt for invisible feathers? You can't use a bucket of xenon for that.
No. There's an experiment called ADMX at the University of Washington. They use giant magnets. The theory is that if an axion passes through a really strong magnetic field, it might spontaneously convert into a photon.
A photon, like a particle of light.
Specifically, a radio wave. So ADMX is basically a very high-tech radio receiver. They're just tuning through different frequencies, scanning the dial, trying to pick up a radio station broadcasting from the dark sector.
That is wild. Are there any other suspects?
There's one that's making a comeback, primordial black holes.
We know black holes exist. We have pictures of them now.
We do, but usually black holes form when a giant star dies and collapses. Primordial black holes are different. The idea is that immediately after the Big Bang, some parts of the universe were so dense they just collapsed directly into black holes.
So tiny little black holes floating around since the beginning of time?
They could be tiny or they could be massive. And if there were enough of them, they would act exactly like dark matter. They'd be invisible, but they would have mass. LIGO, the gravitational wave detector, is looking for hints of these right now.
Okay, I have to play devil's advocate here. I really do.
Go for it.
We've mapped it. We've built the most sensitive detector in history, a mile underground, and found nothing. We're listening for cosmic radio waves. Is there any chance, just a small chance, that we are totally wrong, that dark matter doesn't actually exist?
You're asking about the rebels, and there's a theory for that. It's called MOND, Modified Newtonian Dynamics.
Which basically says,
It says, maybe there is no invisible stuff. Maybe we just don't understand gravity. Maybe when you get to the huge scale of a galaxy, gravity just works differently than Newton or Einstein thought.
you know, I kind of like that. It's cleaner. No ghosts, just a math correction. Why don't we just go with that?
It is attractive.
Yeah.
And for some individual galaxies, MOND actually works really well. It explains the rotation curves, the merry-go-round problem, without needing dark matter at all.
See, I knew it.
But it is a very big but. MOND completely falls apart when you look at the entire universe.
How so?
The biggest evidence against it is something called the bullet cluster. This is a massive collision between two huge clusters of galaxies.
A cosmic car crash.
Exactly. And imagine two cars crashing into each other. The cars represent the gas, the normal matter. When they crash, they smash together and stop right there in the middle of the intersection.
Okay.
But the dark matter, think of the dark matter as the ghosts that were driving the cars. Because ghosts don't really interact with anything. When the cars crash and stop, the ghosts just fly right through the windshields and keep going down the street.
That is a terrifying image, but I get it.
And when we look at the bullet cluster, that is exactly what we see. We see the hot gas from the collision stopped in the middle, but we see the gravity, the lensing way off to the sides, where the dark matter ghosts would have traveled.
So the gravity separated from the matter.
Yes. And MOND cannot explain that. If gravity is just a property of the matter, it should be where the matter is. The fact that the gravity is over here and the matter is over there proves the source of the gravity is something else, something invisible.
So MOND explains the motion of one galaxy, but dark matter explains the entire history of the universe.
That's the consensus, yes. Dark matter fits all the evidence, even if we haven't found the particle yet.
So what does this all mean for us? I mean, for you listening to this on your commute right now, why should you care about invisible glue?
Because without that glue, you wouldn't be on your commute. You wouldn't exist.
Okay, that is a bold claim. Walk me through it.
Think about the early universe. Right after the Big Bang, it was a hot, smooth soup of particles expanding incredibly fast.
Smooth soup. Got it.
If there was only regular matter, that gas would have been too hot and moving too fast to ever really clump together. Gravity is weak. It takes a long time to pull gas together to make a star.
So the universe would have just stayed a misty fog.
For a very, very long time, yes. But dark matter was there. And because it doesn't feel heat or light, it started clumping together much, much earlier. It created these massive gravitational potholes, or wells.
And the regular gas just fell into the potholes.
Exactly. Dark matter created the structure. It drew the gas in, crunched it down, and that's what ignited the very first stars.
So it jump-started the universe.
It accelerated everything. And that's critical, because stars are factories. They fuse hydrogen into carbon, oxygen, iron, all the stuff our bodies and our planet are made of.
Right, we're all stardust.
But without dark matter kicking that process off early, there wouldn't have been enough heavy elements to form the Earth when our sun was born.
So quite literally, dark matter is the midwife of the galaxy. It's the reason we have a planet to stand on.
It's the reason there's structure at all. It's why the universe isn't just a thin, cold mist of hydrogen.
That's actually kind of comforting. It's not just some spooky ghost, it's the foundation.
It really is. And I think there's something profound about the fact that 95% of the universe is unknown to us. We're the anomaly. We are the weird, glowing bits.
So as we wrap this up, where do we stand?
We're in a strange paradox. We can see it better than ever, thanks to James Webb and Euclid. We know where it is, we know what it does, but we still can't touch it.
And we have the LZ detector, which is so good it's finding neutrinos from the sun, but still no dark matter particles.
But that net is tightening. Every experiment that finds nothing tells us exactly where not to look next. We are cornering the truth.
I want to leave everyone with a thought that came up when I was reading through all this. We keep looking for a particle. You know, one thing, like, here's the electron, so
Right.
where is the dark electron?
Right.
We tend to think in simple terms. But look at our world. We have protons, neutrons, electrons, photons, quarks. We have a whole zoo of visible particles. Why on earth do we assume the dark sector is just one boring thing?
That is a fascinating possibility. And it's very likely that the dark sector is just as complex as our visible world. There could be dark atoms, dark chemistry, maybe even dark forces we can't comprehend.
I love that image. We might be like fish swimming in the ocean. We see the bubbles, the gravity, and we know something is making them. But we are completely unaware that there's a whole civilization on the land above us, with its own complex rules.
And we're just starting to poke our heads above the water.
Or maybe we're just looking for a simple answer in what is a wondrously complex universe.
And that's the beauty of science. There's always more to find.
Well, on that note, thank you for joining us on this trip into the invisible.
It was a pleasure.
Keep looking up.